Hi everyone, I'm Indra from Maths University. So I'm a PhD student in applied maths, and I have been using Python for the last 6 years or so. Since my bachelor's. So this talk is about like mostly how I use Python from my day-to-day job and how it has been shaping my career throughout, and why I love Python so much and why I'm in in awe of this particular language, and how much support I get from the community through various resources. Uh, so uh, like if you wanna connect with me through social media, the Twitter handle is like Indranil Ghosh 314, and my website link. Yep. So let's delve in. So this is my career trajectory. I started with a bachelor's in physics. Then I moved on to doing a master's in physics. I was not too much happy about what I was doing. I wanted to do something, related to computational science, more theoretical stuffs, and not many laboratory experiments or something like that. So then I took a slight detour because COVID happened and I had to feed myself. So yeah, and the whole plan got a little bit delayed of what I wanted to do. So I joined a startup company that time, and I was working as a research lead. And eventually, when I had the opportunity to come to New Zealand, and do a PhD in applied maths, I resigned and I started my this PhD job. I'm still a student, so it's not a job, but yeah. Well, yeah, semi-unpaid. Yeah, I have a scholarship, but yeah, it's not that good. Yeah, so okay, so delving more into this. So as I said, I was mostly doing the curriculum that I had in physics. It was mostly the most of the focus was on lab experiments. And the school that I was in that time, the equipments were very old, and I didn't quite enjoy it, what I was doing. So I had to do something which I loved, and I realized that I was a big fan of theory. So I loved solving equations on on a piece of paper, and seeing those equations, the solutions of the equations, in terms of simulations on a computer screen. So I loved computer experiments as well, but not quite lab experiments. So during the summer break, but to do that, to work with simulations and stuff, I had to learn a programming language. And in our course, we were not much emphasized on computer programming. So I didn't learn much computer programming during my first 2 years. And there was a C++ programming element that was there in the last year, which was not, it was very basic. So I had to go for something which I loved. And during the summer break, I still remember I was so happy to come across this tutorial series. Has anyone come across this series before? It's like an MIT courseware, open access tutorial series. So it's by Professor John Goddard. It's the lecture series in computer science and programming using Python. And I immediately fell in love with this. So it was designed for newbies like me, starting from the very basic of not only computer programming, but also the mathematical part. And so I was learning the theory part of physics. I was implementing them using Python. And I was so much happy with seeing the visualizations and all the stuffs that I could do using Python, It was so easy to learn. I didn't need to worry about all the basic intricacies of like the other hard languages. So yeah, so I remember creating a GitHub account. I was so happy. I wanted to showcase my visualization to the whole world. Like very pretty, like very basic simulations and stuff. But still, I was very proud with whatever I was doing. So I just uploaded all my codes and all my visualizations up in GitHub. And yeah, so during the summer time of 2018, there was this opportunity to participate in a summer school, which is called the Dynamics of Complex Systems, which is very far away from what I was studying that time, like in physics. So the basic of this whole school was to teach participants about dynamical systems, mostly ODEs, like ordinary differential equations, and like both in continuous time and also the discrete time version of it, which are called maps. And also like we were taught how to like simulate networks and how to simulate the evolution of this kind of networks over time. It was pretty interesting stuffs that I was learning at that time. So the interesting fact is it was a very competitive school. So the students or the participants had to be selected. So there was a selection procedure, and so they wanted participants who not only had background in quantitative science, but also like they had a background in programming element. So because of my GitHub account, I'm pretty much sure that's what made my CV more interesting to them. So that's why I got selected. And the fun part is I met my like PhD supervisor in this school. So like my current PhD supervisor. So he was one of the lecturers there, and yeah, we networked, and like I fell in love with the topic, which was again very far away from whatever I was studying that time during my master's in physics. And like during that time, I decided, okay, this is what I want to do. I want to use Python from my day-to-day job, and I want to do maths. So not physics anymore. Yeah. So I was supposed to like finish my master's by the end of by the beginning of 2020. But in India during that time, COVID happened. It was terrible, and like my master's degree got delayed. So like I was like, okay, I need to feed myself. Like I need a job. What should I do? So, and I also was very bored. I didn't want to just sit in my house and do nothing. So I taught myself R. I took a detour. I taught myself R, and I created this package called QGame Theory. So this is like a general purpose toolbox for simulating some quantum versions of some game theoretic models. And I submitted this in the CRAN repository. Anyone here has heard about CRAN repository? Okay, cool. So yeah, so it's like I had no idea that like this would be like accepted by them. I had to go through a lot of like screening procedure for that, and so it eventually got accepted. And that time I was looking for some jobs because my PhD, like my master's was delayed, and my PhD program was also delayed. And so I applied to this company, which was a startup company, and they were looking. So they usually, I think, still work with R, and they create like R like softwares and stuff. So they hired me, and they gave me this job to like lead a research team there, and also like lead a software called Shear, which was mostly used to create a linear regression model based on some wind anemometer heights that was provided by the client. So that's what I was doing that time. I was I took a little bit detour, but I was not quite happy again because I wasn't used to use I was not able to use Python. I wanted to use Python rigorously from day to day. So that's why, but I had no choice because the whole program was delayed. And eventually, I got the opportunity to apply for the New Zealand visa. I got I got admitted to the PhD program, and I resigned from this job and I started using Python again from day to day. So, what's my job? So for my PhD, I look into this concept called chaos theory. Anyone here has heard about chaos theory? Cool, cool. Anyone here has heard about butterfly effect? Okay, that's more hands. Yeah, because I think butterfly effect is like more of a like popular term rather than chaos theory. So in my job, so my PhD research is based on that the whatever you are seeing on the left side. So it's a two-dimensional system, and it's like it evolves over time based on this particular rule given by the function f, and it's a little bit complicated looking system, but so this is not an ODE, it's not a ordinary differential equation, as you can see, but it also has two pieces. So depending on the sign of the first variable x, the rule changes. So given by the matrix equations, and this system has 4 parameters. So given by the taus and the deltas, and L represents left piece and the R represents right piece. So, but those are like too much details. Yeah. So what I do is like I look for this concept of chaos, whether chaos exists in this particular system. And this particular system it's a very generalized system, but it has a lot of applications in like ranging from power converters, neuroscience, even climate. I haven't yet worked in any of these applications because my work is more abstract now. But when I go for my postdoc, I am like envisaging to like move towards more applied side. On the right side, the fancy GIF that you are seeing, it comes from this Lorentz attractor. It's a 3-dimensional system, and what you are seeing is like just a 2-dimensional version of the face portrait here. Y against Z. So it's an ODE, it's an ordinary differential equation. And when I say chaos, it means like there are these systems which are very like highly sensitive to initial conditions. So when you like slightly change the whatever simulation you are seeing on the right, so the initial condition for this, if you slightly perturb that, the whole behavior will change like drastically. So like that's what makes the systems very unpredictable. So that's what chaos theory means in general. Yeah. So and as I said, like I look for this particular like in this the system that you saw on the left side, I look for this concept of chaos in particular parameter region. So the top like the colorful pictures are the parameter regions of my system. So the colored region represents the regions where chaos occurs. And we recently like published 2 papers, and the awesome thing about it is like you only use 5 like packages. That's it. The first one is matplotlib. I love matplotlib. It's like it's one of the best visualization packages I've come across. I know there are some good packages in R or other softwares as well, but like I don't bother. So it's matplotlib. And because I'm a scientist, a mathematician, I use SciPy. It's also pretty cool. It has a lot of like functionalities, built-in functionalities, which help like makes my job easier. Then NetworkX. I work with networks as well. So it also helps to simulate a lot of like come up with very pretty visualizations, and like obviously makes the papers pretty cool. NumPy for doing linear algebra calculations, and Pandas for working with datasets. So yeah, these are the 5 core packages that I use almost every day, to be honest. So that's my PhD work, but I am also involved with some other toy projects that I have been working on. So the first one is I work with, I'm a big fan of football or soccer if you're from the US. Like, so with my colleagues in US, we recently wrote this paper called Physics-Driven Study of Dominant Space in Soccer. So what we did is we worked with this GPS dataset freely made available by Metrica Sports. So there have been some studies where they come up with this Voronoi diagrams of each and every player at a particular time on a particular field, which says that those regions are the dominant, dominant spaces for that particular player, where the player would be dominant more than the other players. But usually the Voronoi diagrams have boundaries which are straight lines. But because we included this physics driven kinematic models of each and every player, that's why we come up with these new regions which are not quite Voronoi diagrams, but because they have curves instead of straight lines. So this is one of the projects, and I use Python for doing that as well. But other than that, I maintain a blog which is called Introduction to Football Soccer Data Analysis with Python. So where I try to teach data analysis in terms of football data, using football data and using Python. So if you're if you're new to this field of data analysis and new to using Python, I try to make it very simple to start with. If anyone is interested, please go and check it out and support this blog. Thank you. These are some of the visualizations. So what I'm in awe in is just for football data analysis, there are awesome packages built by the community. This is really awesome. So without the packages, I wouldn't have been able to do these simulations or this analysis kind of stuffs. I use NetworkX, as you can see from the pretty looking networks. That's a past network model for a particular team, and you can come up with very simple analysis those adjacency matrices or the in degrees or the out degrees, very simple stuffs, centrality of each and every team, and so on. The top 2 figures are the passes, and the right one is the shots of a particular player, if I'm not wrong. But yeah, you're welcome to go and check it out. The second project that I'm involved with, here also I use the 5 core packages of Python. So that's Neurodynamics. So what I do is with my colleagues, I try to model the nervous system in terms of very simple network models, as you can see from the right bottom figure, which is a ring star network. The thing is each of these nodes has a particular dynamical system involved with it, and because we couple each of these nodes with each other through this particular network, the whole network evolves over time following a particular rule. And you see a lot of interesting behavior synchronization, desynchronization, even chimera patterns. So where most of the nodes will be synchronized with each other, but some aren't, and those can help study some abnormalities in the nervous system as well. So that's what we do. On the top left, those are the comparison plots between various metrics that we use to study the behavior of the network, synchronization error or cross correlation coefficient, and so on. And the like left bottom half is about like time series, and you can see some chaotic dynamics as well. So this kind of systems usually like exhibit chaotic behavior, and the complexity is very high. So yeah, I have another blog. So this was the topic of my tutorial last year in QEPython. So that was my first in-person like conference after COVID, thanks to QEPython. And like, yeah, this is, so I maintain another blog where I try to teach the concept of mathematical optimization using Python. And it has pretty cool visualizations. Go check it out. Yeah, that's me. And this picture was taken by Christina. I love this picture. This was in QEPython last year. So I love talking in PyCons as well. So I have been talking in quite a lot of PyCons, but mostly like online. But this was the first in-person talk that I have given last year. So yeah, so that's it. So the last slide, I just want to emphasize on the fact that you always don't need to follow what other people are doing. I followed my heart, and this I love this. I love Robert Frost. I love this poem, "The Road Not Taken," and also the other selected poems, of course, but especially "The Road Not Taken." So I did the right thing by, I feel like I did the right thing by following my heart. I was, even though I was not doing quite good in the like experiments portion of during my bachelor's, that's one of the reasons why I couldn't get into a like better university during my master's. So I had to stay in my like my old university. But like, because I was working in Python, I was like showcasing my computational skills, my programming skills. That's why I got the opportunity to go to the school, participate in the school, and meet my supervisor, who only cared about my theoretical knowledge and like computational skills, not the lab experiments portion. So that's why he gave me this opportunity, and I'm quite confident that I have done pretty good. So I'm supposed to submit my thesis by the end of this year, which I'm struggling a little bit with, but hopefully I will finish. And yeah, I have always kept Robert Frost in my heart, and I will always do that. And I know that wherever I go, I'm gonna use Python in my day-to-day job. So yay to Python. And thanks QEPython for giving me this opportunity to talk today here. And I love the community. I love speaking to people. Yeah, thank you so much.
Any question?
Yes, if there are any questions. Yep.
Sure.
So,
Yeah.
do you want me to switch this one off, or?
Is this on? So, somebody said once you can't ask a stupid question. I feel stupid asking it. You had that graph where you were showing your system, and you said this area, the area in green, is where chaos occurs.
Yeah.
So that means the other areas where chaos doesn't occur. Is there a definition of what that chaos area is, or what do you actually define that as?
Let me go to the slide. This one?
No, that one. That one, yeah, that's in there. So you're saying in the green area, we have chaos, outside we don't.
Okay, so I should have mentioned the other figures. So if you can see the four figures, like bottom right. So those, I know it's not very clear, but the black dots that you are seeing, those are like called chaotic attractors. So when I say chaos occurs, that means for this particular system, there will be a chaotic attractor occurring instead of periodic solutions. I don't know how to say that in general term, but it means that if you look into the time series, the one of the indicators is the time series will be very complex, like it won't be regular. So that's the first indicator. And the second thing that you can do to check whether chaos occurs or not, other than the visualization, is to calculate the Lyapunov exponents. Are you ever with Lyapunov exponents? Yeah, so that's the easiest thing to do. So there is this if you use SciPy, so there is this function called scipy.linalg.eig. So if you use that and you come up with the eigenvalues for that particular parameter point, and if the first eigenvalue is positive, that means there is chaos, which I'm seeing here. So yeah, that's one way to see whether it's chaotic or not. But chaos in general term means the behavior would be very complex. It won't be regular. It would be sometimes it would show a lot of spikes, and then it would be regular, and then again spikes. So it could be various phenomenon. You can't say that, okay, this is a particular indicator of chaos. No, you can't do that. So there will be various phenomenon which you can call chaos. So yeah. And also one thing is, as I mentioned, if you see for this particular system, if you change the initial conditions slightly, even infinitesimally, the whole behavior will change. So for that particular parameter region, that means chaos occurs. So yeah, I don't know whether I did a good job, but yeah, these are some of the ways you can check whether there is chaos or not.
Hiya, thank you. So my question was, how hard is it to go from a chaotic state and work back to your initial conditions? Because I know in encryption, quite often they'll have an initial state and then they'll go through a number of iterations where their encryption starts. How hard is it to go from your complex state or your chaotic state and work back to your initial conditions?
Yeah, it is sometimes it could be traceable, but most of the times, because the system is not deterministic, so it might be hard, very hard to go back to the initial condition. So if you trace back, you might end up not the exact initial condition that you started with, but a slight perturbation of it. That's what makes the whole system chaotic in a way. So but that's a very good application in cryptography. I know a lot, even my supervisor, he has worked in cryptography, but I don't have much idea about that. But yeah, I'd be happy to talk to you about this. So yeah, cool.
Thanks very much for the talk. I'm just wondering, from the perspective of working with Python for mathematics, is there anything in particular that you find you wish was easier to do with Python for mathematics, or conversely, is there anything Python does particularly well compared to other languages like R?
Yeah, so I think Ben, when I talked to you last year, so one of the things that I struggle with Python is in this talk I just showed the good side of Python, right? But I struggle a lot with using parallel processing. So I think I talked to you last year as well, but yeah, so that's one of the stuffs I wish it was a little bit easier to use, and because most of my time goes behind studying maths rather than studying the intricacies of the software stuff. So I wish the the documentation revolving Python parallel processing would have been a little bit easier, so that would make my life easier. But yeah, that's what I struggle with. one of the things that I struggle with. And also Python is a little bit slow, so yeah.
Thanks very much.
Thank you. Thank you.